Dear Ola, I'm here again. I'm sorry, but I realized that there was a problem in the registration, in the recording of the of my redoing of the first lecture, the last 10 minutes. So now I will redo. Okay, I will redo the last 10 minutes of my redoing. Okay, and then we will share again the screen here. No, no. I said we share the screen. Ah, okay. We share the screen this way. Okay. Oh, okay. We stopped at this point where I observed that that if you have two Kahler forms, then the Ricci of two Kahler forms eta and omega, then the Ricci of eta and the Ricci of omega define the same cohomology class. Okay, then let's see. Now we want to say what, so we come to the subject of special metrics, and we want to say what a Kahler-Einstein metric is and a constant scalar curvature Kahler metric is. So constant scalar curvature Kahler metric is clear. So what we mean by Kahler-Einstein, a Kahler-Einstein metric is a metric such that the Ricci of omega is a multiple lambda times the form omega itself. And this implies, if you make the trace, then the scalar curvature is constant. So any Kahler-Einstein metric is also a Kahler constant scalar curvature metric. And there is some sort of vice versa. I mean, in general, it's not the same thing. But first of all, we have to say that if Kahler-Einstein metric exists, then clearly Ricci omega and lambda omega must be in the same cohomology class. That means, but we know that actually the cohomology of the Ricci is actually the first Chern class. Therefore, lambda times the class of omega must be the first Chern class. So this is a topological condition which is not always satisfied. However, if this topological condition is satisfied, and if you have a Kahler metric with constant Kahler curvature in that such that the cohomology of the omega of that metric is the given one, then then this metric is Kahler-Einstein. Okay, now we can rescale the lambda because the Ricci of, say, epsilon omega is equal to the Ricci of omega. Therefore, we can rescale the metric and assume and reduce to the case where lambda is either -1, 0, or 1. And however, this topological condition that says the cohomology of omega is a multiple of the first Chern class is not always satisfied. For example, if you take two-dimensional complex manifold, which is a product of two Riemann surfaces, for example, say some hyperbolic Riemann surface times a P1, then this condition will not be satisfied. it's not satisfied. And the construction of the Einstein metric is essentially the subject of this course of Professor Gage. Examples are a flat torus. Torus with a flat metric coming from Cn is Kahler-Einstein because the Ricci is just 0, being a flat metric. Another example is, again, the Fubini study metric in Pn. And here you can see the calculations which show that, I go on quickly, these calculations show that the Ricci of omega is the Kahler form of the Fubini study metric, is n plus 1 times omega. So this is definitely Kahler-Einstein. And also, and now we are done in the sense that I'm giving you some references. Zhang, which is complex differential geometry, International Press of Boston. Then you also have Lazarsfeld, more algebraic geometrically oriented, positivity in algebraic geometry 1, or Claire-Voisin, Hodge theory in complex algebraic geometry 1. And Zachelidi, an introduction to extremal Kahler metrics, or a slightly older one by Gangtiano, also about extremal Kahler metric. Okay, then we are finally done. Hello to everybody. Bye-bye.